Hello, in this video, we're going to be doing an introduction to forces. What is a force? A little more complicated than you might think, but we're going to get into them. And especially we're going to talk about some of the key forces that are in the data booklet, the beautiful IB Physics data booklet. We're going to talk about these, among others. We got your friction force, we got your spring force, Hooke's law, we got a viscous drag force, a buoyant force, force due to gravity. I'll talk about some others and general rules for forces. So here we go. Okay, so first, how do we define a force? Really, our definition can be something simple like this. It's a push or pull exerted on one object by another object. That last part is important. It's one thing pushing or pulling on another thing. And you really want to be able to name the two objects that are involved in the force. If you can't name the two objects, you don't know enough about the force. You want to always think about that. That's a really good concept to keep in mind. It's one thing pushing or pulling on another thing. So we can always define them like this. We'll use A and B for generic objects, but you could do like force of A on B. So I could do like the force of the chair pushing up on me right now, keeping me from falling through the chair, and so on. All right, so that's something we're really going to practice is defining forces that way. Force is a vector, so it's got magnitude and direction when we talk about the quantity. And we measure force in newtons, capital N for Newton. And a Newton breaks down to this. A Newton is a kilogram meter per second squared. The equation, which we'll get into, the big equation F equals ma, is a really good way to remember that unit, since the units of m mass are kilograms and the units of a acceleration are meters per second squared. That's an easy way to remember the units for a Newton, how they break down if you need it. Okay, so what are some forces? One thing you'll see, and we won't talk about it beyond this because it's just generic, is applied force. And an applied force is not really anything special. It's just sort of a generic name if something is pushing on some other thing and it's not something specific like magnetism or whatever. You just call it an applied force. So if I push on a cup, I'm just applying a force. It's just a generic push. I could just call it and label it when we eventually draw these like applied force, FA. Okay, but if it's something specific you want to name it, such as a magnetic force, which would be like a magnet, in this case an electromagnet, pulling on an object. So there we go. We got an electromagnet pulling on a paperclip. Normal force, we'll talk about this, but it's the force from a surface on an object to keep it from moving through the surface. So we got like the force of the table pushing up on that there block. That would be, we would call it the normal force. Lift is another one, which we don't get into too much, but lift is a fun one. How does a plane take off and fly? Well, something must be pushing up on it, for sure, right? There it goes, going up. What could be pushing up on it? I think the only thing it's really touching is the air. So somehow, with some fancy shape of the wing there, it's making the air push up on the wing more than it pushes down, and you get yourself a lift. All right, so always think about the two objects. That's the key thing. All right, one of the weird ones in terms of objects is gravity. Think about this. There's a force of gravity, your weight acting on you, right? So we're going to talk about weight. Weight is basically slang for force due to gravity, F sub g, acting on an object. But again, we always want to name the two objects. So what do you think? What object is pulling down on you right now to create this gravitational force? Well, believe it or not, it's the Earth. It's the entire mass of the planet Earth, which is all down below you, pulling down on you. All right, we're going to get into gravity in detail eventually. One quick fact about gravity is any two things with mass pull on each other, attract each other with a gravitational force. All right. For almost every object, you don't notice it. You don't notice that your cat is very slightly tugging on you with a gravitational force towards the cat, because it's like 24 decimal places smaller than the force from the Earth or something like that. Because the Earth is so big, it's got so much mass, the pull from the Earth on you is greater than any other gravitational force, to the point where we can ignore everything but that. All right, so the Earth pulling down on you is your weight. The Earth pulling down on all objects is the weight of the object, or the force due to gravity. And here's your data booklet equation for the force due to gravity. All you do is you multiply m, the mass of the object, by g acceleration due to gravity, little g. Little g is in the front of your data booklet, as we know. Okay, and so that's how you find the size of the force due to gravity. Most of these force formulas are only going to give you magnitude, only the size of the force, and you have to use your physics knowledge to know which way it's acting. In this case, gravity will always pull down towards the center of the Earth, and we'll deal with later how to account for that in a free body diagram and some fun math. Okay, but that's how you figure out how big your weight is. Do be careful. This gets tricky and sticky, and even the IB is very picky about this, which is fair to be picky about. You don't want to just say gravity if you're talking about like a number, like a quantity. So one thing to really focus on, big concept to focus on, is the difference between the force due to gravity, which is your weight, and little g, which is acceleration due to gravity. This is not gravity. This is not gravity. Just gravity doesn't mean anything. All right, so are you talking acceleration due to gravity, which is always that same number, 9.8, if we're near the surface of Earth. And the force due to gravity is the weight of an object, which, depends on its mass. Okay, so really keep those things straight in your mind, the difference between even mass and weight and acceleration due to gravity and force due to gravity, which is also called weight. Okay, the normal force is a good one. Normal force is another really common one. These are the weight and normal force are probably the biggest two that you'll use almost all the time, because most every situation involves something that has a weight and something that's touching some other object. So normal force is from a surface, and normal is like a fancy math word for perpendicular, which is a little weird, but that's what it means. The normal in normal force really means perpendicular. It is called a reaction force, and there's a couple types of forces like this that we'll see. But what that means is it's a variable force. It can change in response to what's going on, to oppose what we call an action force sometimes. Okay, so we'll look at some examples, but there is no formula for the normal force. This is an important thing. You're going to be tempted to be like, oh, mg, because that happens sometimes. But there's no formula for the normal force. There's no way to just plug in some numbers and calculate. You need an FBD, a free body diagram, and you need to do some net force stuff, which we'll get into soon. All right, so for right now, you can't calculate the normal force until you deal with all the other forces. All right, so here's some examples of normal forces. Let's say you got yourself a bag of dog food, some Bow Wow Chow here, and you drop it on a table. All right, so here we're holding the Bow Wow Chow, and we got the force of the person's hands on the Bow Wow Chow, and we got the force of gravity, which is the earth pulling down on the Bow Wow Chow. All right, and then you drop the dog food, and it hits the table. Then there's two forces. There's the normal force, which is this reaction. It's the table saying, I don't want to break. That's really what it is. It's the table, the structure of the table is stopping this thing from falling through it. So the table will push up on the dog food to resist it breaking through because of its structure. And so that's what we call the normal force. And still the force of gravity is acting. There's no more force of the hand because we let go. In this case, right now, if this is the instant that the Bow Wow Chow is hitting the table, the normal force will be bigger than the force due to gravity. It has to be to stop it and slow it down and keep it from falling through, right? So the normal force will react to the situation. And then very, very quickly, in way less than a second, things will even out. The normal force will get smaller once the Bow Wow Chow is stopped. And after just a second or so, the normal force and the force due to gravity will be equal in this case because we'll have some kind of equilibrium going. All right, but that's what we mean by a reaction force. If you then jumped on top of the table, the normal force would be way bigger than the weight of the Bow Wow Chow because now the table has to push up to stop both you and the dog food from falling through. Here's another one. Let's say you're doing a wall sit, all right, working on your quads here. And there's two normal forces here because normal force is from a surface. It doesn't have to be the floor. That's not the only surface there is, yeah? So for sure, when you're doing this, there's a normal force acting on your feet upwards from the floor. The floor doesn't want your feet to break through it, so it pushes up on them. But also, you're leaning against the wall, and there's another normal force from the wall. Okay, anytime there's contact with the surface, there's a force perpendicular to the surface on the object in contact with it, and that's the normal force. Again, there's no formula for either of these. We don't have a way to without doing an FBD, you can't just get an equation to plug into these. This is not going to be equal to your weight. In this case, it's not pictured here. You got a little friction helping you out. Yeah, this isn't all the forces, just the normal forces. There's a force due to gravity as well, and some friction probably here and here keeping you at rest. Yeah, but there you go. 2 examples of normal forces. It's any force from a surface perpendicular to the surface. Okay, moving on, another common force is tension. Tension is just a force kind of carried, if you want, or within a rope or a cord or a yo-yo string or whatever. And here's some examples. The force of tension at either end of the rope is the same. So you have some situations that look like this. So let's say you're pulling a block with a string, classic physics problem. Okay, however much you pull here, and we have some assumptions here like that the rope is massless, usually stuff like that. But whatever you're pulling with here will kind of be pulled, the rope will pull on the block with that same force. We call it the tension force. Yeah, so picture the tight rope. It will pull the block to the right, and it's also pulling on your hand to the left to kind of oppose, equal and opposite, if you will, to the force of your hand on the rope is the force of the rope on your hand. Okay, same deal here. We got tension both ways. So tension is weird, right? It doesn't have to be like all in one dimension. If I have something like a pulley, I can pull down on the rope here to pull the block to the right because of the magic of a pulley and how tension works. And again, this force will be the same, and same deal here. You could do it this way, and then both tensions are up. Fun, but that's just because it's this way on the rope and then the other way on the rope. All right, so that's what we mean by directed along the cord or along the rope. Okay, so there's tension again. That's one that you'll need an FBD to figure out everything else going on and find the size of the tension force. Okay, and another of the really common forces is friction, and friction is fun. It's a little complicated because there's 2 types, so we'll talk about it. All right, so friction is what we call a resistive force. It's one of a few different resistive forces that we're going to talk about. And really what it is it acts on a body from a surface to slow or prevent sliding. So those are really our 2 types of friction. There's a type that slows it down if it's moving, and there's a type that stops it from moving if it's at rest. When we say a resistive force, this is what we mean. It's a force that opposes motion, but we want to be specific when we say that. And really, to get the direction of a resistive force, it's opposite the direction of the velocity vector. Not necessarily displacement or anything like that. It's just opposite velocity. So to find the direction of a resistive force, you look at the velocity vector, like which way is that thing moving? The force is in the opposite direction. So usually these are pretty simple and intuitive, like if a thing is sliding and moving to the right, friction will be to the left to slow it down. And again, this is pretty intuitive, but the friction force is always parallel to the plane of contact, which just means like if you have a box on the ground, the friction force is along this plane. You know, it's along the ground horizontally. So I got a horizontal plane of contact. I have a horizontal friction force, something fun like that. Okay. Here's a good little picture of what's going on with friction, and here's a animated one. So here's really what's happening with friction. It's because of the 2 surfaces in contact. If you zoomed way in at like the microscopic level, you know, a piece of wood, nothing really, is totally perfectly, completely smooth. It's got these little imperfections in the surface. So it's kind of the roughness, if you will, of the surface will tell us about how big friction is. So in this case, you know, how rough the boxes and how rough the floor are affect friction. So we do have a number to sort of represent that. But this is sort of the idea of why, you know, there's some resistance when you try to move something. Okay, so the first type of friction is dynamic friction. This is friction associated with something in motion. Sometimes we call this too kinetic friction. The IB goes with dynamic. They mean the same thing. It just means something moving. If it's moving, it's easy. Use this formula. Bam, that's how big friction is. All right, so the size of the friction force acting on an object when it's moving is this formula, data booklet formula. You got this little guy. This is the Greek letter mu with a D subscript to see dynamic. So we call this the coefficient of friction. In this case, the coefficient of dynamic friction. And really what it is the friction force is proportional to the normal force. And it's proportional by this kind of a ratio scaling factor, this coefficient. If you want, the coefficient tells you how much friction force you get for every, like, certain, let's say, Newton of normal force. Yeah, so normal force, if the surface is pushing up on the object a lot, picture those little microscopic bumps. Maybe it makes sense that you're going to get more friction, more resistance. And this accounts for the two surfaces. That's really what you want to think about. It has no units because I got newtons for friction and newtons for the normal force. So this must be unitless. So it's really a unitless ratio. And again, it really is, if you want to think of it this way, it's the ratio of the size of the friction force to the size of the normal force. Yeah, but it really has to do with the roughness or the smoothness of the things. So like, a hockey puck on ice has a very low coefficient of friction, like 0.07 or something, let's say. Whereas, that box on the floor would have a much higher coefficient of friction, 0.3, 0.4, something like that. Yeah, so it's just a measure of the two surfaces in contact. You could either solve for it or be given it. It's one of those things that just depends on the two surfaces. Another type is static friction, and this is friction for something at rest. So static friction will be when something's at rest. Picture pushing a couch like lightly and it doesn't move. You can feel a force resisting you. That force is static friction. Static friction is a little more confusing, complicated, let's say, because it's a reactive force, much like the normal force. This is another example of one of those. It reacts to the situation. And what it is, it can take any value up to a maximum. So our formula for the static friction force looks like this. It's an inequality. So fun. The rule is the force of friction. And let's get into this. This will be, in this case, in this context, that's the static friction force. Again, the magnitude only is what this equation will give me. Is up to, can be any value up to is what this means. This coefficient of friction, again, times the normal force. So same formula, really. The only difference is we do have different coefficients for static and dynamic friction, so that's one thing to watch out for, be careful with. But what this implies is that there's a maximum, and really a lot of it's going to come down to that, is calculating a maximum. So this would mean, so therefore, the maximum force of static friction, FF smax if you like, is equal to this much, right? Because that's the biggest value that this could be. That's what the inequality means. So this is what you're going to often calculate for friction, because this will tell you what's the biggest amount of force that this thing can like resist starting to move with. Yeah. And whether or not there's enough force, other forces being applied to the object will tell you compare it to this to see if it's moving. All right. So you can use this one to figure out whether or not it is moving. So you do it like this. You calculate that maximum force of static friction. So, all right, let's think about how this works then to put it all together. If an object is at rest, this is a kind of complicated little graph, but it's a good one. It might even show up on an IB test or something. Great graph to conceptually understand friction. If you know what's going on with this graph, you pretty well understand friction. Okay, so this represents, y-axis is the force of friction, and the x-axis is like an applied force. All right, so I'm like, say, picture the block on the floor, and I'm pulling on it with an increasing amount of force until it starts to move. All right, well, if I don't pull at all, there's no friction force, and there's no applied force, so there's no friction force. Right? If I don't try to move the box, there's no friction that needs to stop it from moving. If I apply, let's say, 1 Newton, if I pull with 1 Newton of force, then the static friction that would oppose me would be 1 Newton. It reacts to be equal to the applied force up until some maximum. Okay, so let's just say the maximum force of static friction is 10 Newtons. Okay, just making it up. It'll be different in every situation. All right, again, if I pull with 1 Newton, it resists with 1 Newton. If I pull with 5 Newtons, it resists with 5 Newtons. Okay, it's like, smart. It reacts to what's going on. If I pull with 10 Newtons, that's the cutoff. And so right when I'm there or above it, I guess that's the maximum. So if I pull with 10 Newtons, it's just able to still stay at rest if that's the maximum force of static friction. And any little bit above 10 Newtons, if I pull with 10.0001 Newtons, or 11 Newtons, then this thing will start moving because now I'm over the maximum force of static friction. And what happens then, if you're moving, remember this, the friction force just is this big. All right, so as soon as you get over that maximum static friction force, the thing starts to move and your friction force becomes some constant value, no matter how much you push or pull. So this never changes. The static friction force, though, will equal your applied force unless you're applying more than the maximum static friction, in which case it's moving, in which case you use this for friction. Okay, so that's probably seems like a lot of rules. It'll take some practicing with to kind of get used to that, but that's the idea. You figure out if it's moving or not. That tells you which of these formula to use. You never use both. It's only either static or kinetic. If it's at rest, you use the static one. If it's moving, it's kinetic. And also notice the graph looks like this because the coefficient of kinetic friction will be less than the coefficient of static friction. Again, picture little bumps and see if you can picture why that would be true. Why is there less resistance when the thing is already moving compared to when you're trying to get it moving? All right, so that's friction. All right, there are more forces in the data booklet, but that is plenty for right now, so we'll call it there. All right, now you go think about it. Have fun.